Today we are going to go over 8.3, the integral test and the p-series test. Last lesson we learned the Nernst test, for divergence. So that means if the limit as n go to infinity, a of n, when the limit is non-zero, this tells us the series diverges. This is only test for divergence of a series. The integral test. So what does the integral test tell us? So if the a of n, the nth term f, we take it as a function of n here. If f is positive, continuous, and decreasing, in this case, the series and the integral here, okay, the series from 1 to infinity and the integral from 1 to infinity, fx dx, they either both converges or they both diverges. So both of them, they have the same property. So instead of studying the convergence or divergence of the series, we can evaluate the integral. If the integral converges, then the series will converge. How do we prove the integral converges? So if the integration from 1 to infinity f dx equals a number, in this case, this will converge. So if the integral converges, then the series will converge. However, keep in mind, they have the same property, but they are not equal. It's not equal to the sigma n equals 1 to infinity a of n. Some students might have another question. If this n doesn't start from 1, for example 2, it doesn't really matter, n from any number, this will work. Let me go over 2 examples. If you look at this function, this is our function f of n, so positive, decrease, and continuous. Let's have a look. Integration from 1 to infinity. We are going to replace n using x squared plus 1 dx. So if you look at this integral, this is improper integral because one of the boundaries is infinity. We are going to use what we learned in chapter 7 to solve this problem. So if you look at this problem, we can use u substitution. So u equals x squared plus 1. So du will be 2x dx. So the whole problem will become 1/2 ln x squared plus 1, 1 to infinity. Now we can plug in the limit as x goes to infinity. 1/2 ln x squared plus 1 minus, we plug 1 in, so it's 1/2 ln 2. As we know, as x goes to infinity, x squared plus 1 goes to infinity. ln infinity gives us infinity. So infinity minus a constant, so the final answer will be infinity because the integration is not a number. So the series diverges too. So the integral diverges. So the series diverges too. Let's have a look at this problem. So let's have a look at n start from 1 to infinity. So first, in the future when we see a problem, first let's have a look. As n go to infinity, n over e to the n squared. Does Nernst test work? So as we know, as n go to infinity, so this will be 0. So the Nernst test doesn't work. So let's see, can we use any other test? For now, we only learned the integral test. Let's have a look if the integral test is going to work. X, we replace n using x. So in order to evaluate this, we are going to use u substitution. U equals x squared. So du will be 2x dx. This will be integration. So when we integrate this, we don't need to worry about the boundaries. So this will be 1/2 e to the negative u du. It's negative 1/2 e to the negative u. The integration will be negative 1/2 e to the negative x squared 1 to infinity. So now we are going to use limit as x go to infinity. Negative 1/2 e to negative x squared minus, we plug 1 in, so it's negative 1/2 e to the negative 1. As n go to infinity, so 1 over e to the x squared goes to 0. That would be 0 minus, this will be a negative here, minus 1/2 e to the negative 1, give us 1/2 e to the negative 1, which is a number. The integral will converge. So the integral converges, so the original series will also converges. I'll give you 5 minutes to finish these two problems and compare your answers with mine. These are the answers for these two problems. Everybody have a look. Make sure you are okay with the solution, especially for arctangent. If you forget, this is the picture for arctangent, for tangent, to help you to evaluate tangent inverse. And once again, the integral and the sigma, the sum, they have the same property, but they are not equal to each other. So the second part of this lesson will be the convergence for p-series. So for p-series, it's very special, similar to as geometric series. We can identify the convergence or divergence of this type of series. Just look at the power here. So sigma n goes from 1 to infinity, 1 over n to the p. Keep in mind, p is a constant here. And what is changing here? N is changing. N changes from 1, 2, 3, 4, 5, 6. So for this type of series, we call it p-series. So if the power p is greater than 1, then the series will converge. And if p is between 0 and positive 1, include 1, this series will diverge. When p equals 1, sometimes we call it harmonic series. So this will give us a very easy way to solve this type of series. Just look at the power. For example, when n goes from 1 to infinity, this one is 1 over n to the 1 over 5. So p equals 1 over 5 less than 1. So this gives us the series diverges. Let's have a look at this function, 1 over n squared. As we know, p equals 2, which is greater than 1. So the series that will converge. So if you look at this one, the only difference right now, the n starts from 3. It doesn't really matter n starts from 2 or 3 or 4 or 5. As long as it's p, okay, equals 2 greater than 1, so the series will converge. The only difference between these two is the final answer will be, it will converge to a different number. So this one will be equal to n from 1 to infinity, 1 over n squared. If you look at these two, so this series is missing two terms, when n equals 1 and when n equals 2. So we can minus n equals 1 and n equals 2. So this is the relation between these two numbers.